In this chapter, we will be covering basic IP packet structures, their headers, and payloads. In the chapter, we're going to cover Internet Protocol version 4, so IPv4, and version 6, IPv6, their packet structures, including various header fields, and how they allow IP packets to perform complex functions that permit information to traverse different network environments, including the Internet. IPv4 and v6 headers are compared, and we're going to learn how the packet structures in each version of IP operate, including the different capacities of each. The objectives in this chapter, we're going to identify the various fields and features that make up an IPv4 header. We're going to do the same for an IPv6 header. We're going to talk about the purpose of IPv6 extension headers and the function of each header. We'll talk about MTU discovery, how it works in IPv6, and how it replaces fragmentation of IPv4 packets by routers. We're going to talk about the upper layer checksums, how they work in IPv6 packets, and the use of pseudo headers. And we're going to explain the primary difference between v4 and v6 packet structures and why the differences are significant. So first, when we talk about IP packets and packet structures, again, this primarily transmits and delivers data between devices on networks. But for it to work, each packet needs to contain a header structure containing a number of specialized fields in addition to the data. So in this section, we're going to talk about the structures of IPv4 and v6 packets. You're going to have a general knowledge on this topic, and we're going to help you better understand TCP/IP and networks in general and how they work. But we have to remember IPv4 and IPv6 packets are going to differ significantly. So let's begin with IPv4 headers and functions. So in the figure 3.1 that is in the slide here, it shows the basic IPv4 header structure offset by the number of bits. So again, you need to get familiar with this concept and the structure, the limitations on length of each of these. So first, if we flip back, you may want to flip back, print this slide off as we talk about each of these header fields. So the version field is the first field in the IP header. It indicates the IP version 4, so it is IPv4. Again, with all of these, I'm going to flip back to the previous slide, follow along with the bit offset. So again, when we're talking about a whole header here, the version starts at 0 and is populating bits 0, 1, 2, and 3 of the header. Again, each of these are fixed in length unless otherwise specified. So that's the version field. Again, the field itself has a value of 4, so that indicates that it's IPv4. The header length field, we also call it the Internet Header Length field, or IHL field. This denotes the length of the IP header. So this length says the header is going to be this long. It includes an offset to the data to make it fall on a 32-bit boundary value. The minimum length for the IHL is 20 bytes, and the maximum length for the IHL is 60 bytes. So again, if we flip back here, the header length begins at bit 4, 5, and goes through bits 5, 6, and 7. So I'm not going to do this for all of them, but remember, make sure to flip back, look at your header structures. If you're reading as well, do the same. So the TOS field function, this is differentiated services and congestion control, so it's specified in RFC 2474. It recommends a complete redefinition of the older TOS field values and functions. And what it does is defines a method for differentiating services for network traffic using the 6 high-order bits of the byte that was formerly the 3-bit precedence field and the first bit of the TOS field. So it shows differentiated services code point identifier. So again, it prioritizes traffic by an end device, node, or boundary device. So it uses a special marker, that's the DSCP, and again, it can be prioritized by an end device or boundary device, so a node or a router, and it can be queued and forwarded according to that value. So routers that support the differentiated services technology would handle traffic according to the DSCP identifier. Differentiated services are relevant for real-time applications, so you're talking chat, instant messaging, online gaming, and video conferencing. So kind of going back here, RFC 5280, it updates some of the terminology. The previous RFCs for the DSCP were RFC 3280 and RFC 2474. So again, these breakouts show the various fields, what flags can be used for the TOS field. The total length field, this defines the length of the IP header and any data. So it is the total length. The identification field. So each packet has a unique ID value when it's sent, and if the packet has to be fragmented, the same ID number is part of each fragment. Think about the reason for fragmenting an IP packet, and again, the identification field kind of helps put all the fragments together. The flags field is 3 bits long, so again, we'll flip back. So your flags field operates on bits 16, 17, and 18 after the 32-bit offset. If fragmentation is allowed, a packet has to be fragmented across a network that supports a smaller MTU, or minimum transmission unit. The don't fragment bit is set to 0. So again, you set these fields for how the packet might be fragmented. So if the packet is fragmented, you're going to use the fragment offset field. You're not going to use it otherwise. And it shows where to place this packet's data. So when the packets are reassembled and the fragments are reassembled at the destination, this helps the destination to know what order to put it in. And the offset is in 8-byte values. The time to live field, or TTL, you'll hear TTL a lot. So the TTL is the remaining distance that the packet can travel. It denotes the number of hops a packet takes to go through routers on its way to a destination. It's defined in terms of seconds, but the value is implemented as a number of hops. So typically a starting TTL is either 32 or 64 or 128. The maximum value of TTL is 255. The protocol field is used by IPv4 packet headers to specify what type of information is on the packet's payload, so the destination host can correctly process it. So as we show in the table here on the screen, some of the common values of the protocol field. So for instance, it can be an ICMP message or an IGMP message, a UDP message, a multicast transport protocol message. Based on what protocol it is, you put the value within the protocol field of the header. The header checksum field, it provides kind of an extra level of error detection in addition to the error detection performed by the data link layer. So it's required for packets that pass through routers. The source address field is how it's named. It's the IP address of the IP host that sent the packet. It can't contain a multicast or a broadcast address, but if the address is unknown, you can use 0.0.0.0. The destination address, the same as the final destination of the packet. It is the IP of the destination, and this can include a unicast, multicast, or broadcast address. The options field, so you can extend an IP header using the option field, and it provides additional IP routing controls. Your options must end on a 4-byte boundary, and they exist to provide additional controls. So here's an example of various options. You can specify end of options list, no operations, security, timestamp, as well as a number of other options here. So again, keep these for your reference as you're trying to look at headers. So padding. So padding is used to make sure that the header ends at the 32-bit boundary. So it consists of a bunch of zero filled bytes just so that it can end on a full 32-bit boundary. So just a bunch of zeros. So IPv6 headers, fields, and functions. So again, your IPv4 and IPv6 are going to be different, but the purpose of both are the same. The purpose of both an IPv4 and an IPv6 packet is to ensure the data or application information is successfully going from a source to a destination. In IPv6, there's some improvements. We have enhanced support for extensions and options, and they're designed to make it easier in the future to update some options. So here's the header structure for an IPv6 header. You'll notice this is a different structure from IPv4, so you'll want to reference this header structure when building out or trying to evaluate an IPv6 header. The version field is a 4-bit number, and in this case for IPv6 it's 6, so the binary of 0 in the first position, 1 in the second, 1 in the third, 0 in the fourth position from right to left. So your traffic class field, this is an 8-bit field, and it's used by source network hosts and forwarding routers to distinguish the various classes or priorities in IPv6 packets. So the packet could be delay sensitive, it could have a specific precedence, and there's reserved values that can be used in the future. So similar to IPv4, IPv6 also supports real-time applications and non-default quality of service, so you can use the flow label field for that. The request for comment 6437 is the proposed standard for flow labels and that specification, and in that spec it defines the min requirements for this field. The value of the flow label is 0 for packets that have not been labeled. So if you're not yet labeling the packet, just label it 0, and if the nodes don't support it, they have to ignore this field. The payload length field is 16 bits. It describes the size and the payload in octets. When the length is equal to 0, or length is equal to 0 when the hop-by-hop options extension header has a jumbogram option. The next header field is a completely different addition compared to IPv4, and it specifies the header type of the header immediately following the IPv6 header. So when IPv6 uses extension headers, this field points to the first extension. It also allows for headers to be chained together after the basic IPv6 header. The hop limit field is similar to time to live in IPv4. So it's an 8-bit field. The max value is 255. It decrements one time each time it's forwarded by a node. The source address field is the 128-bit IPv6 address of the source of the packet, and same thing with the destination address field. It's the 128-bit address of the recipient. This may not be the final recipient of the packet if there's a routing extension header. So IPv6 extension headers They allow additional functionality to be implemented in an IPv6 packet. So a packet can still remain small and streamlined, but possess only the field that's required for a particular purpose. Each extension header is identified by a specific next header value, and extension headers must be processed in the required order, and that we'll look at in the next session. So, header ordering, defined by RFC 2460. Here is the recommended order for the extension header. So either hop-by-hop options, and then destination options, then routing, then fragment, then authentication, then ESP, then the destination option. You can see the header ordering in the diagram here on the screen, what the chain headers look like. So now we're going to go through the various extension headers and what they mean. So hop-by-hop options. This header allows maximum flexibility in the header definition and functionality, and it's designed to carry information that affects routers along a path. So you can see how this is designed in the figure on the screen. The destination options header provides a method for extending the IPv6 header to support options for packet handling and preferences, and it's the only header that can appear in more than one location. Destination options header uses the same format as the hop-by-hop extensions header. Next is the routing extension header. It supports loose or strict source routing for IPv6. And you can see how to use the routing extension header to support strict or loose source routing as shown in the diagram. Your fragment extension header. So, while IPv6 doesn't support fragmentation at forwarding routers, if a transmitting device needs to send packets that are larger than the path MTU or PMTU, the IPv6 fragment extension header is used. So in figure 312 that's on the screen, you can see the fields of the fragment extension header, which are almost identical to the IPv4 fragment fields, except for the use of the flags field. Next is authentication extension header. I'll get my slides to work. So security is one of the huge design goals of IPv6. So proof of this is the authentication extension header. It specifies the true origin of a packet and has an integrity check on the parts of the packet that don't change in transit. So your ESP, or encapsulating security payload extension header and trailer, this is used to encrypt the data. Previous extension headers helps with authentication and integrity, but it doesn't offer confidentiality, a means of encrypting the data. So we use the encapsulating security payload to offer that confidentiality to give you the full CIA triad. This header must always be the last header of the IP header chain and indicates the start of encrypted data. So you can see in the figure how that is designed. So Jumbograms. So Jumbograms, they use the hop-by-hop options extension header to add an alternate packet length field of 32 bytes. This allows the packet to carry a single chunk of data larger than 64 kilobytes, anywhere up to 4 billion bytes. So the name Jumbograms is a huge datagram. So quality of service, what's quality of service? It's the ability of a network to provide better service to specific types of network traffic, and it's handled by the DiffServ working group at the IETF. So differentiated services are what quality of service is all about. The concept is simple. It should be possible to choose and pay for something other than the default level of service. If you want video to have a higher priority than audio on your network, if you want video to have a higher priority than data on your network, you can do that through QoS. And the concept is simple. It might be assured delivery, it might be expedited delivery, temporary assignment of unusually large bandwidth, low latency, lowest delivered cost, maybe at the expense of quick delivery, or any of several parameters of value to certain users or certain groups of users at different times, at different places. It's extremely flexible. So you use the resource reservation protocol as an early attempt, or that was an early attempt to have a more formal approach to dynamic resource evaluation on the internet. But that's kind of the overview of quality of service. So router alerts and hop-by-hop options. So IPv6 recognizes and responds to low demand for differential or differentiated QoS, but it still makes provisions for its gradual adoption. So the IPv6 header eliminates all the fields relating to QoS which were carried in the IPv4 header. Instead, it allows options headers such as hop-by-hop, the routing extension header, the destinations options extension header, as flexible ways to implement current and future QoS schemes. So by eliminating fields in the basic IPv6 header, which would have to be examined by every single router, IPv6 speeds up the processing of the default QoS on the internet. When you create headers that can be examined by all or by selected hops on a path, IPv6 creates tools that can be used by QoS protocols to gain precise control of per hop and per domain behaviors. So IPv6 MTU and packet handling, so that's covered by RFC 1981, and it's the definition, it defines the mechanism by which IPv6 discovers the MTU of an arbitrary network path. We called that the path MTU before, the PMTU, and the PMTU discovery process. So IPv6 nodes, they execute PMTU discovery to learn which network paths have a greater maximum link MTU value. Once we found a path and discovered the MTU packet size is set, packets can still be routed across different paths, and packets can encounter network nodes that cannot manage the MTU size. So upper layer checksums in IPv6. Any upper layer protocol containing addresses from the header in the checksum computation must include the 128 IPv6 address. So when we're running UDP over IPv6, the checksum is mandatory, and a pseudo header is used to imitate the actual IPv6 header. So again, this is the IPv4 header, and we just want to compare the different packet structures. So here is the IPv6 header, flip back to an IPv4 header, and you can see the changes in the transition between IPv4 and IPv6. So this is a nice little table that you can use that helps compare IPv4 and IPv6 headers. Good reference guide to have. And then the IPv4 to IPv6 transition, so RFC 3056, oftentimes you'll hear it called as 6 to 4. It's an optional method for IPv6 sites to communicate with IPv4 networks without setting up tunneling, but it's prone to misconfigured nodes. There's a transport relay transistor, or TRT. It allows IPv6 network nodes to send and receive TCP and UDP traffic with IPv4 network nodes. So these are just some summaries of transitioning and cross-communicating between IPv4 and IPv6 networks. So again, some summary of the things we covered and that the book chapter covered. The IPv4 header fields have been the method of providing reliable sending and receiving of data on networks for decades. So again, we talked about the history in Chapter 1, why it was created. Well, if we have a nuclear blast, we can still communicate because we don't care about what path we take. We want to make sure reliability, the sender can get a message to the destination. The IPv6 header structure is a lot simpler than IPv4. It performs the basic function, but it's different in that it uses extension headers to add back or add special functionality back to the packet. The various extension headers, we talked the hop-by-hop options extension header. It carries data that affects routers along the network path. Jumbograms, Big datagrams, special type of IPv6 packets that use the hop-by-hop extension header to add an alternate packet length field to the packet. IPv6 MTU discovery, or we talked about PMTU discovery, ability of a source node to discover the maximum MTU size, and upper layer checksums are mandatory when running UDP over IPv6. And while the IPv6 header is larger than the IPv4 header, it's mainly because it covers a larger address space. Remember, the IPv6 source and destination address each take over 128 bits, compared to 32 bits in the prior addresses. The significant differences between IPv4 and IPv6 packet headers illustrate these protocols' incompatibility. You have to punctuate the difficulty in transitioning a worldwide network infrastructure to the latest version of IP. So that's the overview for this chapter. Good luck this week on the chapter and the quiz. And if you have any questions, please let me know.